I got lucky this time. So I think last time we were finishing this problem here, and we did this one. We did one like this with the quadratic formula. In fact, we sort of looked at two there. So it involves using the inverse trig functions. So I think that I got you up to the point where we were actually solving it. We solved it. We said that one of those roots was over 1 or less than -1. So we threw that away. And then we would use the inverse cosine to solve the other one. So I think we were almost done with that. I just had you finish that one up. But since that's the last example in 6.2, were there any questions on that one? Did you want to see anything worked out there? No. Okay. All right. Well, then without further ado, let's get into the last section here. So what we're doing in this last section is we are going to look at trig functions with multiple angles. So we're going to solve for those trig functions with multiple angles. We already saw a technique on how to handle these. If you have like a double angle, you can, most of the time you can substitute in a double angle formula and get everything in terms of one functions. But what if you have like a triple angle or a quadruple angle, something like that? Then that technique's not going to work. So we want to see how we would handle those. So really what we're going to do here is our strategy is going to involve solving for the double angle. So let me scroll down here. So when we have equations involving multiple angles, here's sort of our strategy. We're going to solve the trig equation for the function of a multiple angle. Okay. So we're going to start by doing that. Notice the first one's already solved there. So we can sort of check out our technique here. So we've already solved this one for the trig function of the multiple angle. So what we do then is we're going to go ahead and take the inverse trig function of both sides. So if I was solving this one, and this would take us back to 4.7, that one we did before the test, but this is a really good application of those inverse trig functions. So I'm going to go ahead and take the inverse trig function of this. I'm going to solve it for that triple angle. So we solve the trig equation for the function of a multiple angle, and then we're going to use the inverse trig function to get all those solutions. Now this one happens to be a special value, right? It's quadrantal. So we want to know where on the unit circle is cosine equal to -1. So we can either use a calculator to get an answer and then convert it over to the angles that we need, or with these special angles, we can actually figure out where that is. So where is cosine equal to -1? What angle? And it looks like we're dealing with degrees here for this one.
180.
Yeah, exactly. And that's the only place, right? So great, it's quadrantal. Good job. So -1, 0, -1 is the cosine. Excellent. So the only place from 0 to 360, we find all those places. The only place is 180 degrees. Okay. So what we know now is that 3 theta is equal to 180 degrees. Okay. So here's the new part that we're using. So what happens when we have that 3 theta in there? So let's think graphically. What happens when we have that 3 theta in there to the trig function? What does that do graphically?
Affecting the period?
It affects the period. That's right. So it's going to speed it up 3 times as fast, right? So instead of completing a cycle in 360, it's going to complete a cycle in 360 divided by 3, right? 120 degrees. Yeah, exactly. Good. So that's something that we have to think about here. So when we're solving for a multiple angle, nice. Since this is 3 theta, our period is now, instead of 2 pi or 360, it's going to be 120. So this is what we have to do to find all these angles. Once we find everything on 0 to 360, we're going to add on right away 360 degrees times k. Okay? We're going to find all of them. And of course, k is an integer here. So now we can go ahead and solve for theta. So when I solve for theta, I just divide both sides by 3. And I find out that theta is equal to 60 degrees plus 120k, 120 degrees k, where k is an integer. And I'm just going to use that fancy notation this time. K is an element of Zelen. Okay, so see what's happening here. If I want to find all of the answers on 0 to 360, if I have 1 for the triple angle, how many do you think I will have on that interval for the single angle? What's your gut feeling? You can show me. You can show me with your fingers. Let's use the clean ones. Okay. I see one person showing me. How many do you think? What's your gut feeling? So if the triple angle has 1, how many do you think the single angle is going to have on 0 to 360? Okay. I've seen 2 sets of fingers there. Okay, there's 3. Any more? Any? Yes. Okay, thank you. All right. Any other guesses there? Okay, I think most of you had it there. That's right. We're gonna get 3. We're gonna get 3 angles there because, like we said, this speeds up. And so what we can do here to find those 3 is just let k be the values of 0, 1, and 2. So let's try that. So really what you can do is just start plugging in values of k. And when you get too far, then you can stop, okay? So if I plug in 0, I'm going to get 1 at 60. When I plug in 1, I'm going to get 60 plus 120, and that will be 180. So it turns out 180 is actually an angle there that works. When I plug in 2, I get 60 plus 240, and that's going to be 300, I think. And when I plug in 3, I get 60 plus, let's see, 3 times 120 is 360. I get 420, but 420 is too much, and it corresponds to 60 here. So those are the same angles, they're coterminal. So I don't have this one because I'm just looking for the ones here. So this formula here would give me all of them, but I was just asked for the ones between 0 and 360. So these 3 would be the ones that we were looking for. Now, I want to show you something about these roots geometrically that we're going to be looking at a little bit later in the class. These will always be evenly spaced. So notice that we have one here at 60 degrees. We have one here at 180 degrees. And we have one here at 300 degrees. Notice that this sort of cuts the unit circle in 3 equal parts, right? So these will always be geometrically appealing as well, okay? So if we have a triple angle, we would triple the number of solutions for our single angle there. If we had a quadruple angle, we would quadruple the number of solutions there. But that's sort of the idea. So we solve for the trig function first. We use our unit circle, our special trig values, or the calculator if they're not, to find all the special angles on 0 to 2 pi. so the natural period. And then we add on that 2 pi k, or the 360k, and then we go ahead and divide and find all the solutions on that interval. So that's sort of the process that we're using there. Are there questions? Okay. All right. So that's about it. That's about as easy as it gets. So let's try another one here. And this one, you know, it's already solved for a trig function, but it's solved for cosecant. So we have cosecant of a double angle. Now, you know, we could actually, if we know a lot about cosecant, we could use cosecant of that, but we probably want to use the idea of the reciprocal function, right? So we would replace cosecant of 2 theta by what?
One over sine, or the sine. Would we use this the double angle or no?
So 1 over sine 2 theta. Yep.
Yeah,
We'd use that double angle. Nice job, Emily. Yeah. So we'd replace that cosecant, great, by 1 over sine 2 theta. And yeah, we have to keep that angle the same. Is equal to -2. And now what we want to do is we want to solve for sine 2 theta. So at this point, I can go ahead and multiply both sides by sine 2 theta, sort of like we did in the other section when we had one of these alternate functions. I'm just going to go ahead and do that. And let's see what we have. We have 1 is equal to -2 sine 2 theta. And then finishing up to solve for sine 2 theta, I divide by -2. So I have sine 2 theta is equal to -1/2. Okay, so I solved the double angle, the trig function of the double angle for -1/2. Now I'd like you to take a very short amount of time to figure out what angles we have on 0 to 360, okay? So I'll give you a minute or two. And so I want you to find all those angles on 0 to 360 for 2 theta. So 2 theta is equal to what? So what you probably want to do is make a triangle, and you want to figure out what quadrants the sine is negative in, and you want to draw out that triangle and find those angles. Okay, so give it a try. And this again is where your mastery test will come into play. Okay, that was only a minute or so. Does anybody need more time to figure those out? Okay, you got it. You got it. Perfect. So this will be exactly what you're doing on Thursday. So I want to make sure that you're there. Yeah, take your time. Nice job. Well, actually, one of them's right. Ollie. Think about that one in the fourth quadrant. Okay. All right. So that's 2 minutes. So let's go ahead and discuss this. So there you go. Caleb, what 2 quadrants are we dealing with here where sine is negative?
3 and 4.
Excellent. Nice job, Caleb. So I'm going to just draw those in here. And remember, I'm dealing with 2 theta here, but I don't know. I could just call this some other angle like x maybe. So x is equal to 2 theta. Great. And so sine is opposite over hypotenuse, right? So I have a 1 to root 3 to 2 triangle. Okay. And I have this over in the fourth quadrant as well. All right. So, Katie, do you know the reference angle there?
Sorry. I do not.
Okay. So what kind of a triangle is it? A 1 to root 3 to 2?
Well, it's 30, 60, 90, right?
Exactly. That's right. And notice that the angle we want to find, it's across from the smallest side. So what's the smallest angle?
30.
There you go. So good. So x is going to be x hat. That reference angle is going to be 30 degrees. All right. Excellent. So 2 theta in quadrant 3, what is 2 theta equal to? Jonathan?
105 degrees.
What was that?
Oh, quadrant 3.
Quadrant 3.
210 degrees.
Perfect. 210 degrees. And Michaela, in quadrant 4, what is that reference angle going to be?
330.
330. Perfect. I misspoke there. What is the angle going to be there? 330. But you know what I was saying. Wow. You can read my mind. It's a little scary. No. Good job, Michaela. All right. So we found those 2 angles for just plain x, right? But now we have 2 times that. So what we want to do is we want to add on the period 360 for sine times k. And then finally, we want to divide by 2 to find that actual angle. So I'm going to divide both sides by 2. And then you're right. Okay, so I see where you got that 105. Good. So theta is going to be 105 plus 360 divided by 2 is 180k. And over here, when I divide by 2, theta is going to be 165. Is it 165? Okay, thanks. 165 plus 180k. All right. So that is going to be all the angles. That's going to be all the angles. So if you just wanted all the angles, these would be your solutions. But of course, Thursday, I'll want you to find the ones on 0 to 360. So, okay. So with these, uh-oh, am I losing you? I hope I'm not losing you. Okay. Okay, you're back. With these 2, oh, my internet connection is unstable. All right, so hopefully I don't lose you. If I do, then I'll come back. How many angles should we have on that interval? You can give me a visual again. 10? 8? How many should we have? How many should we have on that interval? Now remember, we found 2, and it's a double angle. So I'm talking about all of them together. Yeah. Yeah. 4. Yeah, great. So we should have 4. Excellent. So we knew that because it's a double angle. So however many we have here, we just double it. So we have two single angles here, so we double each one of those, so that's 2. Okay, so now we just plug in values of k to find the 2. Great. So when k is equal to 0, we have for the one in quadrant 4, we have 165. And when k is equal to 1, we have 165 plus 180. 165 plus 180, 24, 345, hopefully. Yeah, that seems right. Okay. So those are going to be our 2 for the one in quadrant 4. And so for this one, totally running out of space here. Wow. No. So here, when k is equal to 0, I have theta is equal to 105. And finally, when k is equal to 1, I have theta is equal to 180 plus 105. That's 285, right? So these would be the 4 that I'm looking for here. And we should see that those are going to be evenly spaced. Now, these are going to be evenly spaced with respect to each other. So let's find them. 105, that's going to be over here. And so 285 is going to be down here. It's going to be a reflection about that origin. 165, that's going to be over here at about 180. And then 345 is going to be just opposite like this. So those aren't totally symmetric because they came from 2 different angles there. But you can see that they're symmetric with each other. Okay? Questions there? Okay, great. Nice job, Aiden. You had it too. All right, very good. So let me clear this out. Aha. This one looks weird and sort of bad. So I have sine of 2x, cosine of x. Cosine of 2x, sine of x is equal to 1/2. That one looks like I have double angles and single angles in there. Wow, how am I going to do something like this? It looks like the last one I changed secant and or cosecant into its reciprocal, right? Is there any way we can condense this one down into something nice? Go ahead, Ali.
Gonna be sine 3x equals 1/2. So it's sine 2x plus x. Give us
Exactly.
Mhm.
Very nice, very nice. So Ali, notice that this one from the chart you'll get, those angles you'll get. Nice, nice job. This is actually a formula for the sum of sines. So it's sine 2x plus x is equal to 1/2. So we have sine of 3x is equal to 1/2. And this is because of that double angle, or I'm sorry, sum of sine formula there. So sine of A plus B is equal to sine of A cosine of B plus cosine of B sine of A. Excellent job. All right. So now we should be able to solve for those, right? So let's go ahead and do that. Nice job. So where is basically I could say 3x is equal to inverse sine of 1/2, but I can use triangles to figure that out. So I would go ahead and say sine is positive in quadrant 1 and 2. So let's go over here, 1 and 2. I'm just making my triangles here. Sine is going to be opposite over hypotenuse. So it looks like this one's going to be another 30 degree, right? But now I'm in radians. So instead of 30 degrees, what would that be in radians? What's the reference angle there, everybody?
5/6.
Yeah, great job. So x hat is equal to pi/6. Okay. So we have pi/6 there, and we have one there. So in quadrant 1, we have 3x is equal to pi/6 plus 2 pi k. And in quadrant 2, where sine is positive, we have 3x is equal to 5 pi/6. So it's going to be pi/6 minus or sorry, pi minus that pi over 6, right?
5 pi over 6.
5 pi over 6 plus 2 pi k. So we use that reference angle to find that angle. So if we're over here at pi over 6 or as a reference angle, we know that pi is going to be 180 degrees. So we take pi minus that. Great job. And then we could get a common denominator. 6 minus 1 is 5, pi over 6. Okay, so how many angles do you think we'll have to solve for on that interval now? Use your fingers. I want to see everybody's fingers. Okay, you're gonna have enough. Okay. I see one good answer there. There's 2, yeah. Okay. More, everybody? How many, or type it in chat. How many do you think you're gonna have there? All right. Ben, Benjamin, you're a little dark in there. I can't see your fingers there. How many do you think? Oh, there we go. Okay. So we have 2 here, right? But they're tripled. It's a triple angle. So everybody that was doing 6, we'd have to use 2 hands this time. 6 is correct. So let's see how that plays out. Nice job. Okay. So I'm going to divide each one of these by 3. And so x is equal to pi over 18 plus 2/3 pi k. And down here, when I divide by 3, I'm going to have x is equal to 5 pi over 18 plus 2/3 pi k. So again, when k is 0, I have, of course, x is equal to pi over 18. When k is 1, I have pi over 18 plus 2 pi over 3. Wow, I should have just kept it as a common denominator there. So maybe I should do that. Multiply each of these by 6. So that's 12. 12 over 18. 12 plus 1 is 13. And finally, when k is 2, I have double 12. That's 24. 24 plus 1 is 25 pi over 18. All right. Just for fun, let's see what would happen if I plugged in 3. So I'd have 12 times 3. That's 36. 12 times 3 is 36, right? 36 pi over 3, which would be 12 pi. 13. Okay, I made a mistake somewhere there. 37 pi over 18. That would be too much, right? 37 pi over 18. That would be corresponding to this one. So yeah, we only get 3 for this one. Or we get all of 3 there. And then we'll do the same thing for this one here when k is 0. We have 5 over 8 pi over 18 when k is 1. So again, I'm going to get a common denominator here. Take this times 6 and this times 6. So I'll get 12 plus 5. 12 plus 5 is 17. 17 pi over 18. And then finally, when k is 2, 2 times 12 is 24. 24 plus 5 is 29. So I'll have 29 pi over 18. And then I should have too much if I go further. So when I look at the first ones, pi over 18, it might be like here, 13 pi over 18. That one's going to be over here somewhere. And I know that they're evenly spaced out. So this is really going to be 2 pi over 3 or 120 degrees between them. And 25 pi over 18, that one's going to be down here. So there's the first 3. And when I look at those second 3, 5 pi over 8, that's going to be somewhere in here. And then I add 120 on that. 17 pi over 8 is going to be almost 180 degrees. It's going to be almost pi. And 29 pi over 18 is going to be over here in quadrant 3. Well, that's pretty. So we will have those 6 solutions there, and you can sort of see them graphically on the unit circle. Questions? All right. All right. Let's do one more. I'm gonna clear this out. Okay. So this one we have a quadruple angle, and we have this squared. So this would yield itself to either the quadratic formula or the square root method to solve for the sine. So I can actually just go ahead and take the square root of both sides. So when I take the square root of both sides here, I'll have sine of 4x is equal to plus or minus the square root of 1. So sine of 4x is equal to plus 1, and sine of 4x is equal to minus 1. Okay. So Benjamin, where is sine of x equal to 1? What angle is sine of x equal to 1 at?
It's a quadrangle angle at 90 degrees pointing upwards.
Excellent. Right on, man. So I guess it doesn't really specify whether we're in degrees or radians. Benjamin, I'm going to give you your choice. Which do you want to do, degrees or radians?
Radians.
Okay, yeah. X usually stands for radians. Okay, so nice. So pi over 2 is going to be the only one here where sine of an angle is equal to 1. All right. Let's see. Who haven't I called on? Tomas. Where is sine of x equal to -1? Sine of something equal to -1.
270 degrees or 3 pi over 2.
Excellent. Very nice. So this one is 0, 1. So that's where sine is equal to 1. Excellent. And then Tomas has angle down here, 0, -1. That's where sine is equal to -1. It's the only spot. 3 pi over 2. Excellent. Very nice. So we have here, and I'll move this one over here. 3 pi over 2. So I'm going to add on the period of sine. All right, so we have one more chance here. How many angles do you think I'm going to have in all on the interval from 0 to 2 pi? Yeah. Yep. We're going to have 8. We're going to have 8. Nice job. Nice job, everybody. So we're going to have 8 there. So you know what? It says find all solutions. So really we're almost done here. So all we have to do is divide by 4 to find all those solutions. So all of the solutions would be at pi over 8 plus 1/2. Okay, pi over 2, okay. And then this one's going to be at 3 pi over 8 plus pi over 2k, where k is an integer. So that's going to be all of them. If we wanted to find those, we can, it's going to be pretty easy to label them graphically. So we find our one at pi over 8, and then we just go 90 degrees across, 90 degrees, 90 degrees, 90 degrees. So that's going to be, those are going to be where the first ones are. And if we look at the second one now, 3 pi over 8, that would be about right here. So 90 degrees, 90 degrees, 90 degrees. So that would look sort of like a pinwheel there. Those are all evenly spaced. In fact, you could probably find all of them with one equation to sort of like put those together, but what we have there is perfect. So I guess if you really wanted to put them together, wouldn't it be something like pi over 8 plus pi over 4k? I think that would do it. Pi over 8 plus pi over 4k, I think would get you everything there. Okay, so you see the symmetry there. All right, great job. Any questions on multiple angles there? So you see the process. We want to solve for the multiple angle, add on the period, and then remember how many angles you're going to have on that period, divide it by the angle and find them. Plug in k to find them all. Okay. All right. So excuse me, with the time we have left, I do have something else we could do, but do you have any specific questions for the test or anything for next time? I'd like to help you out. So anything in terms of what's coming up on that test? Questions about the test? Questions about the math contest tomorrow? Sure. Nothing. All right. All right. So I would suggest that if you have time, look through that extra credit review, try some of those, and I promise you that I'll give you those other ones back on your test day. So I'll see you all there on Thursday. Okay. So you know that I like to look at some applications. So I was gonna show you an application of what we've been doing. Let me see if I can find it here. All right. So I think I'm sharing my WebAssign now, right? It's actually going to be a variation on this projectile motion. So if you look at that picture there on your screen, so a projectile that's fired into the air, we can actually find an equation for the height of that object given any time. And in fact, if you go along in the calculus sequence, you'll see why that first term is added in there, the -16t squared and the vt times the sine of t. When you think of that projectile as a vector, you might think of like, hey, the height is going to be that velocity times the sine of that angle, right? That's going to give us the vertical component. And then that -16t squared, that's actually due to gravity. So the gravitational pull on the Earth. Again, in calculus, you'll look at this more. In fact, we are skipping the parametric equation section, but you know, if you wanted to also find this range here, like how far it went in the x direction, you could actually find a formula for that pretty easily. You could say that x would be equal to v times t cosine of theta. And actually that doesn't have anything to do with gravity there. So if you wanted to see like how far downrange that object would go at any time, it would just depend on that launch angle and the initial velocity there. Okay, so I want to try to share a Desmo screen. Oh, let's see, new share. Let's hope this works. Boom. I don't have Desmos open. Oh, they did. Okay. Sorry. Okay. All right. So I want to look at the graphing calculator. Am I sharing my Desmos there? Okay, great. Thank you. Thank you. All right. So okay, open graph. There we go. Okay. So I want to take a look at a couple of questions here. Oh, I didn't want to undo that. that are sort of listed there. So we looked at that graph there. A projectile is launched into the air with an initial velocity v given by the function below with the angle theta. So we're going to pretend it's a bullet or something like that. So like when people celebrate, sometimes like they celebrate a big soccer victory or the 4th of July, sometimes they like shoot guns in the air. Don't ever do that, because that bullet has to come down somewhere, and it's going to come down with the same velocity that it is if you would have just fired it like coming out of the gun. So we're going to be looking at a projectile that's fired into the air at some angle, and it's given by this function. I wanted to use t there for the input, but Desmos won't let me. So just sort of pretend that those x are going to be t's in seconds. So let's look at projectile fired at 1500 feet per second, and the angle theta is 30. We want to find the function h of x and the maximum height of that bullet or that object that's fired there. So if I plug in 1500 for v, I think that that's stored in here, and I use pi over 6 for theta. So I could plug that in there. I think that it'll let me do that. So pi over 6 for theta. I get some graph that looks like this. So that v is going to be 1500. Let me just plug that in for now. We have a graph that looks like this. So if I sort of zoom in a little bit, what does this graph look like in terms of the projectile motion? What does that look like? Does that look like anything familiar that you've studied before?
Parabola.
It's a parabola, exactly. So that's going to be a parabolic function. So it turns out once you plug in things for the angle, if you plug in the initial velocity, this projectile motion, the height is in a parabolic sort of shape, because the height varies with respect to time, but also the range is going out. So this shows a pretty good picture of what's going on. So you might remember we have this equation now. We know that sine of pi over 6 is, what is sine of pi over 6 again, or 30 degrees?
0.5.
Yeah, 1/2, 0.5, exactly. So our equation becomes h of t is equal to negative 16 t squared. Let's see, half of 1500, that's 750, right? 750 t. So that's going to become our equation now. So I want to find the maximum height. Now in calculus, you'll look at finding the maximum and minimum of functions using the derivative, but there are some that you might know the maximum of, and a parabola is one of them. Do you remember how to find the maximum of a parabola? Where is it found? What is that point called? Do you remember what the point's called? At the top or the bottom? What if I give you a hint? It starts with a V.
Vertex, right?
There, yeah, that's right. Vertex, exactly. Nice job. So we want to find the vertex of this parabola. And there's a special formula for the vertex. Anybody remember? That's the only reason, that's the only way I can find this using the skills that we have right now without calculus. So that formula for the vertex was x, or t in this case, was equal to, you'll remember when I write it down, negative b over 2a. Maybe? Does that ring a bell, sort of? Yeah? Okay, all right. So in this equation, what is the b? What's the b in this equation?
Is it the 750?
It is. And what's the a?
The negative 16.
Exactly. Great. So I can just plug that in and compute it and find the time. So yes, nice job. So negative 750 over 2 times negative 16. I'm going to get my trusty calculator out over here, although I probably could do it in Desmos. So let's see. Negative 750 divided by negative 32. I got about 23.4375. So it looks like after 23.4375 seconds, we're going to reach that maximum height there with the vertex. How do I find the maximum height? How would I find the y value? Just sort of stick that in h, right? So let's go ahead and do that. So I'm going to try down here to stick that in h. So I'm going to do h of 23.4375. And it looks like the maximum height here, wow, it's going to be about 8,789 feet. All right. So maybe I could even plot that to see if that actually works out. So what if I just stick a y equals in there? Oh, okay, great. So it does look like it calculated that maximum height there. All right. So I thought that was sort of cool. So we could find the maximum height here, but we can also look at some other things here. So let's look at B here. If a bullet is fired with an initial velocity of 1,500 feet per second, and it takes 3 seconds to reach 750, what was the launch angle theta to the nearest degree, 1/10 of a degree or radian? So I'm going to go ahead and clear this out for a minute. So if I wanted to find the launch angle for this, I need to plug in everything I have to figure out what that theta was. So I'm going to go back and put this theta in here. And 1,500 is still going to be my velocity. So that function looks good. So if it takes 3 seconds to reach 750, then I can make an equation for that, right? So I can say h of 3 is equal to 750. And I can plug in wherever I see x. And I know that that's going to equal 750, right? So I plugged in 3 for the time, and I know that at that point, it's going to be 750. Well, I should be able to solve this equation and figure out what that launch angle is based on that point. So let's try it. So let's see if we can't figure this out in our last few minutes here. So 3 squared is 9. So I have 9 times 16. I'm going to need some calculator help here. So negative 144 plus 1,500 sine theta. Oh, but I have it times 3, so that's 4,500. Sine theta is equal to 750. And now it looks like a linear equation I can solve. So I have 750. If I add over the 144, I have 4,500 sine theta is equal to 894. So I add that 194 over, and then I divide by 4,500. So now how do I solve for that angle? What do I do?
Inverse sine.
Great. Okay, so this is another place where we need to use the inverse. Excellent. So this is going to be positive. So it's going to give me an angle in quadrant 1. And that's really what I'm looking for. So I think I'm in degree mode, so I'm just going to stick there. I'm going to do inverse sine of 894 divided by 4,500. And I got about 11.459 degrees. So 11.5 degrees launch angle should give me that equation. So let's just check that out and see if that gives me the data that I want. So I'm going to plug in, let's see. Oh, I need radians for that though. So I can just multiply by pi over 180, right? So that's about 0.2 radians. And there's my equation now. Okay. So in this case, my equation looks like that. And if I want to find what's happening after 3 seconds, hopefully after 3 seconds, it should be 750. Let's just see. 1, 2, 3, up 750. Yep, that's where they intersect right there. So I just wanted to show you some applications of this new theory that we're working with. So hopefully you enjoyed that. Maybe take it to heart a little bit. You'll probably see something like this, you know, as one of those questions that makes you think on the test. Okay. All right.